we have arranged the electro-optic setup as shown in the manual, and then we align this electro-optic crystal along with, so that light beam passes accurately along the axis of this crystal. So, after that we remove the analyzer and we rotate the first polarizer, so that light passes through the polarizer with the maximum intensity. After that we place the analyzer and we rotate the analyzer, so that the light transmitted through it is minimum. After that we turn on the DC power supply, which is connected to the electro-optic crystal. Then we will increase the voltage from 0 to 2 kilovolt in steps and measure the light reaching the detector at each step. First we start with the 0 input voltage and the corresponding output current is 0.4 microampere. Then for 0.1 kilovolt the current is 0.4 microampere, and for also 0.2 kilovolt the output current is 0.4 microampere. Then 0.3 kilovolt correspond to 0.5 microampere and 0.4 kilovolt correspond to 0.5 microampere. Then 0.5 kilovolt correspond to 0.6 microampere. Then 0.6 kilovolt correspond to 0.8 microampere. 0.7 kilovolt correspond to 0.9 microampere. 0.8 kilovolt correspond to 1.1 microampere. 0.9 kilovolt correspond to 1.4 microampere. 1 kilovolt correspond to 1.6 microampere. 1.1 kilovolt correspond to 1.8 microampere. 1.2 kilovolt correspond to 2 microampere. 1.3 kilovolt correspond to 2.2 microampere. 1.4 kilovolt correspond to 2.4 microampere. 1.5 kilovolt correspond to 2.5 again. Then 1.6 kilovolt correspond to 2.4 microampere again. 1.7 kilovolt correspond to 2.4 microampere. Then 1.8 kilovolt correspond to 2.3 microampere. Then 1.9 kilovolt correspond to 2.2 microampere, and at last 2 kilovolt correspond to 2.1 microampere. Here you can notice that the output current increases up to a point of input voltage, and after that the output current decreases with increase in voltage. So you have to plot the intensity variation as a function of input voltage, that is, you can plot a current versus voltage graph. From the graph you can determine the half wave voltage and extinction ratio. Half wave voltage is the input voltage correspond to maximum transmission, that is, it is the input voltage correspond to the maximum output current, and the extinction ratio is the ratio of the output current correspond to half voltage to the output current at 0 input voltage. After that you should also have to plot birefringence versus applied voltage graph. For that you can calculate the birefringence using the equation dN is equal to lambda divided by pi into L sin inverse of P of V divided by P of V half, where lambda is the wavelength of the laser we have used, that is 633 nanometer, and L is the length of the electro-optic crystal we have used, that is 2.5 millimeter, and P of V is the meter reading at voltage V, and P of V half is the half wave voltage.